Good afternoon, ladies and gentlemen. In my talk, I would like to talk about the influence of the surface treatments on the tensile fatigue properties of nickel titanium wires and springs made from superelastic nickel titanium. Actually, we are collaborating with several companies. One of them is LRCS. It's a manufacturer of stents and medical devices. The second one is Fort Wayne Metals, producers of nickel titanium structures, and they actually want to test their own processes which they want to apply and applying on their wires or structures. And we are already developing several years some methods to simulate, let's say, the stents or the complex loadings which are applied on these stents. So we bring an idea to create samples in form of helical springs, which somehow has similar complex loadings, torsion, bending, tension, and we usually also with them testing also these straight wires. So to move on, I will just show you the fixtures which we use for manufacturing of these helical springs. As you may see, this is pretty tiny fixture. It has like 3 millimeters in diameter, and afterwards there were applied the treatments which I will talk later on. So with the springs, we actually achieved removing localization. We obtain quite easily obtainable samples. Also, they are not so expensive as stents. In Fort Wayne Metals, actually, Jeremy Schaffer create nice homogeneous treatments with their 200 microns in diameter wires samples in form of helical springs and straight wires. What was nice that we have really nice controlled composition, cold work, and quite nice homogeneity of treatments. The wires which I will spoke in the second part of my talk are mainly used in SEM testing. This is experimental setup which we develop and operating in our laboratories. You may see there is electrochemical cell, let's say, but in this study we use just water. We can control the temperature, which is pretty necessary for any shape memory alloys, and otherwise you will get bad results, mainly in case of fatigue. So we tested, we also control the temperature of load cells, because in case of helical springs we are dealing with very small forces. So to avoid some drifting during the time, we try to control the temperatures even of our equipment. Data control was an acquisition was done by LabVIEW and National Instruments Electronics. So to move on, I will just show you how the treatments looks like. First one is just as drawn wires. There is cracked surface, then it's heat treated. So it's just cracked surface of wire, and on top of it, it's just ground nature oxide, thermal oxide. Treatment number 2 is just heat treated wire and then electrochemically polished. Treatment number 3, it's something which they call silk method. It has ultra fine roughness, and then it's applied thin oxide layer. In treatment number 4, it's just heat treated wire etched, so probably it looks exactly like this wire before the treatment, then it's the surface etched and then microblasted. So you may see there is pretty rough surface. Just from the AFM measurements, I would like to point out that the, let's say, original surface, it's like 20% larger than, has larger surface area than the rest of us. So maybe in some medical application it could play some role in point of chemistry or let's say resistance to some environments. To move on, we did some thermomechanical characterization of our helical springs. So these data are for the helical springs. You may see and observe that They are not completely the same in force position diagram, but I may told you that at least the treatment number 2, which is electropolish, has a slightly different diameter, so maybe just due to the diameter change, the force it's not so high for the rest of the treatments. These are the SEM curves for all of the treatments. You may see that in low cycle fatigue regime there is no significant difference. Maybe there are small difference between these samples with oxide and without oxide, but it's questionable because there is really small number of cycles still failure. So to move on, we can proceed to the fatigue limit area, and you can see and observe that in this knee is probably the microblasted samples shows nice resistance to fatigue. And in the high cycle fatigue, we actually stopped these tests so they could continue all for each treatment. To go further, I will just show you the fractured surfaces. This is just one side of the helical spring, but every time we look on each of both sides of fractured surface and try to characterize it, but what was clear pretty much soon, we found that at the inner side of the helical springs, it was larger tensile stress, and there, from this point, the crack will appear for regardless the treatment. So you may see that the tensile stresses are probably pretty bad for our material. So more on, we also try and test these treatments on applied on the wires. There is not so significant differences at stress strain curves. We may compare it with the helical springs response. So what I will now show you what's happening already during tensile test in the SEM upon loading. So you can see that there is you will see some red arrow propagating up here. Yeah, it's just there is Martensik transformation occurs and just propagating through the whole wire. So this state is just changing of the phases from, let's say, 1% in maximum in austenite to the, let's say, 6 to 8% in martensite. So this area I will just show you. This is schematic area. It's not like it's not something which is real, but during the tensile test of each kind of structure, it's just damaging the surface of oxide, which cannot sustain these stresses, and it's quite brittle. So we think that something which we call martensite band front is propagating through the wire. When you have something similar, let's say a ribbon, there is something also some Martensik transformation propagating, but for wires it's really nicely symmetric. Now I just talk a bit about the surface treatments upon loading. This is every time it's just first cycle in the SEM, and you will look on exactly the same area. For treatment number 1, it's quite hard to find some cracks because it's already cracked. So you may see that there will be something which I will just mark by arrow, small crack, but when you load it into the martensite, now the crack just open. So this is happening every time. For every each case, you will stretch a new wire into the martensite, unload and load again. So these cracks will open gradually. So for treatment number 2, of course, during the first cycle, because the treatment number 2 is electropolish, and there is non-oxide, or let's say maybe native oxide, which could be like 10 nanometers or really thin, you cannot observe it under the SEM. So we didn't observe during the first cycles, or let's say hundreds of cycles, any changes on the surface. For treatment number 3, however, there is a large field, hopefully you can see it, a large field of cracks, because there is a thin oxide layer, the surface underneath has a really low roughness, so it fractures gradually, and I will talk a bit more about it later. And for treatment number 4, where probably there is applied some residual stresses due to the microblasting, but the surface is quite damaged, there are already existing grooves, or you may say cracks, which just open upon loading. So this is just an example of surface area with thin oxide layer. This is just first cycle in martensite. It's cracked almost everywhere. There are small, tiny cracks with large density. But when you are cycling furthermore, it's cycled in strain regimes, strain control regime. So you will see that the propagation of these cracks inside, probably into the matrix. So to conclude my talk, we tested 4 different surface treatments. In water, we obtained these Wöhler curves. The oxide layers during the cyclic deformation shows that they are actually cannot sustain the deformation even during the first cycle. Cracks in oxide layer, I can just tell that it's really good to observe them in situ in the SEM, otherwise you are not able to see them at all. And the cracks nucleate on the inner side where the largest tensile stresses are applied in the helical springs. And surface finishes, let's say, I would just point out that the microplasting surface, probably due to the residual stresses in the surface area, just helping and somehow moving the fatigue resistance of these helical springs. However, the thin oxide and, let's say, ultra-fine polished surface on the samples doesn't help at all and actually enhance the damaging process. So thank you all, and if you have any questions, feel free to ask.